We see the ocean floor here in California, the Juan de Fuca plate going under the continental plate. This is what we call the intrinsic method. The lava is coming in, perforating here, perforating over here, and goes down into the lava. There is more pressure here than here because of the depth. You see the height, the depth, and therefore this may sustain itself, the flow going automatically. And we start heating this plant. Not too much, because otherwise if it becomes solid, it's not going to be possible to do that, to put it back. The extrinsic method, it will be actually using the lava to create maybe bridges. Conceptually, will be a huge crane that takes the lava. The lava will go like this and will be dropped there. This is another example what to do with the lava. Over here, this is the duct. The lava comes to a huge crane. It could be as long as 300 meters long. And you see, dropping the lava there, this is the ocean, you see. We could be building a structure like a barrier. Imagine this is the coast of Florida and there is flooding. This is the cranes. These are the cranes, right? And this crane will take care of building, extracting the lava and building this. And this one does like this, and this one does like this. And with a series of cranes, we might be able to very inexpensively, in relative terms, instead of building this with concrete or with granite, that would be really practically impossible, very expensive to bring all that granite from the Rockies, let's say. But with this, extracting the magma, we can make this kind of barrier. It could be also used to make a bridge, okay? In some places where maybe there is an island here, and it will be very costly to make a long bridge, as long as 30 miles long. A way of building bridges much less expensive than building the way that we build today. So this is like an additional technology, that will branch out of this extraction of lava. Some miles of fissure where the boundaries are spreading, the lava is coming up. We got volcanoes, plenty of places where we don't have to perforate, so we can use a tunnel, build a tunnel in some areas where maybe there are more active areas, tunnels that could be 10 kilometers long, and then close that tunnel because it has lava coming up. It's going to be boiling water that we insert in that tunnel. If we can overcome the difficulties of, in some of these places, the ocean is 7 or 8 kilometers deep, so the pressures are huge. But at the same time, that pressure also helps us where we don't need to make any, the structure can stand on the floor by itself without having to be nailed down to the bottom of the ocean. Let's say that this is the ocean floor, and this is the mid-Atlantic ridge, for instance, and this is the fissure where the cave is slamming up. The worm will be building over here, or inside the ridge or outside, depending on the situation. But let's say for now, to make this thing easy, it will be structured like this, all right, covering that, and then closing in the corners. The vapor will build up over there, and then through pipes taking the vapor to a turbine, which is a turbine that is floating on the top of the ocean like this. This is the cross section, all right, of the worm, and this is the pipes taking the high pressure superheated vapor all the way to the bars where the turbines are, generating electricity, and then in cables taking that electricity to the shoreline. How to build this structure over here? Is that easy? We have to make, huge semicircles, basically like this. Maybe build those on the beach with some molds. In the interior they will be empty, so they actually will float on top of the ocean. So, you see, the worm is made out of a lot of sections. Some, of course, it will be closed in the ends. And it could be as long as 1 kilometer or maybe 10 or 20 kilometers once we master the technology. We could start first with 300 or 400 meters. And each module, these building modules, they have to be bolted into the bottom because first of all, let me explain. We make this on the beach, and with barges, we carry that to the place where they have to be dropped. They have a density that actually, because they are empty inside, you see the cross section over here, these modules, they lock and they are empty, so they float actually, they can be carried on the top of the ocean. And then at that particular place is being dropped because you know, we put some food, some shoes into the module, so that increases the weight and it just drops there. Now when we start sucking the water, when we finish and we start sucking the water, right now it's in isobaric pressure, meaning the pressure inside is equal to the outside, so it's not difficult to just put it in place. But as soon as we start sucking the water, pumping the water up, now the exterior pressure is much higher and this becomes stuck to the floor with high pressure. Remember this is 8 kilometers, maybe 7, anywhere from 6 to 8 kilometers depth in the Atlantic Ocean. And at that depth is huge pressure because every 10 meters in the ocean floor, every 10 meters of depth is about 1 atmosphere. So if we are talking about 8 kilometers, it's 800 atmospheres. So it's a huge, huge pressure. So this will be really smack against the, you know, in this case you see it has been built within the ridge, all right? And the pressure from the water, the outside, we just leave some water here that is going to be hidden by the lava. It's going to be, you know, superheating that water. We just leave a layer of water there. It could be salty or it could be fresh water, so they doesn't accumulate salt there, deposits. You know, we can remove all the water from that tunnel and then put fresh water, and that's it. Once in a while we replenish with more water, but we don't need to put much water because we don't lose anything. It's just vapor coming out, you know. And we might extract, with the extra heat, we might produce clean water that we can insert, so we don't have deposits there. But, you know, every 50 or 100 years, we might have to replace or relocate to a different place the tunnel. We might have to allow water to go in, so it becomes isobaric. Again, and when it's isobaric, you just can remove it. As if we flood the interior with water, the pressure becomes equalized, and then we just can remove it and move it to someplace else in case of the lava came up and now the lava is filling up the space in some areas where it's very active. But being so hot and being so much pressure that no much lava is going to come out. And eventually that happens, we will relocate this to another place. Or you just remove it from the floor, because this is just standing there. Doesn't need bolting. It's just the pressure that keeps the thing in place. And they're easy to install and easy to remove. That's, you know, this is the part that I thought it was going to be difficult, and I thought it was not feasible. And now this, I think, is where the most, out of the 3 alternatives, this is the more scalable and the more feasible, all right? Easy, because making a dock that is very deep, it might be challenging, really challenging. And right now we have difficulties making a bore that is drilling more than 15 kilometers in the crust. In some places we have to drill even 20 or 25 kilometers. All right? But with this alternative we have to drill. Well, there is drawbacks, risks, of course. It's a new frontier of technology. It's high-tech, very comparable to the high-tech that NASA has. There is a significant initial investment. It might take 10 years to get a significant progress during the learning curve. As I explained, it could be a desired accidental eruptions that might occur. Should NASA be looking up or looking down? That's the question. No question that looking up has been, you know, it's very interesting to discover for astrophysics and for our knowledge of our planet and other planets. At this particular point in the history of the civilization, it's more important, you know, to send a probe to Pluto and maybe a rover to Mars, or is more important, you know, those billions of dollars which are well spent, no question about that, all right? I used to work for NASA. I used to work for a subcontractor of NASA, Aeronautical Laboratories on Long Island, New York. It is, what we are doing is great. As an engineer and as a scientist, I love, you know, the probes and the effort that NASA is doing to discover the mysteries of the universe. The government should create another agency like NASA, or redirect the efforts of NASA to start looking down as well. Because that's the place where it's plenty of energy. But it's going to take some technology to get there and to extract that energy, all right? But plenty it is, clean it is. And explore, you know, trying to extract that heat, that vast amounts of heat from the interior of the Earth.